Professor Deborah Johnson, and for those of you that don't know me, I'm the Pro Vice Chancellor Academic Framework here at London South Bank University. So it's my pleasure to welcome you all to the inaugural lecture of Professor Sandra Dudley. So the presentation of an inaugural lecture is a significant milestone in the career of a former professor. The inaugural lecture provides an opportunity to do several things: to present their career so far, to introduce their field of expertise to a wider audience, and to update colleagues on their current and future plans. So for the schools where the professors are based, the event has manifold impact, manifold good things. So it's a chance to celebrate this achievement with other staff and with students. It's a chance to strengthen existing relationships with alumni, with old friends, and it's a chance to establish new conversations and new collaborations. So for the university, for LSBU, it's very simple what an inaugural lecture does. It represents an essential way that we show the value, the wider public value of our research, our teaching, and our knowledge creation. And so as such, we are delighted to be restarting in our inaugural lecture series. After a break because of COVID, we are back, and we have had several inaugural lectures in the last couple of months. So please do go to our YouTube inaugural lecture playlist. Now we are meeting in person again, and that feels really special. And it's really appropriate because it gives us a chance to do several things. So after the lecture, we'll have a reception, and that means we can be flexible, we can talk and converse. It also gives a chance to have that richness, that deeper understanding of being here in person. And importantly, it gives a sense of gravitas for what is a very special milestone. Meeting in person also gives me the chance to give that age-old introduction to any face-to-face event, and I guess we haven't missed it. I'm sure we haven't missed it. So let me start. Please switch off your mobile phone. Keep in mind we are recording this event. The toilets are right outside, and we are not planning a fire alarm. So if the alarm goes off, please, in an orderly fashion, follow the fire exit signs. We haven't missed that, have we? So, let me now introduce to you Professor Dudley. And there are several ways that I could try to do this. So I could give you a potted history of Sandra's academic career. So Sandra Dudley is a Professor of Communication Systems and received her BSc and PhD in Physics at the University of Essex. Following her PhD, Sandra worked with Essex University and British Telecom, producing a world record low-power cabinet system for low-energy installations. Following that, she joined London South Bank University's Department of Electrical and Electronic Engineering as a senior lecturer. I could tell you about Sandra's research topics, and her research interests have charted laser design and characterization, optical communication systems, sensing, low power systems, and applied AI for communications and remote energy monitoring. Her interest in wireless system design and characterization has led to exciting collaborations on human tracking, health monitoring, and recently gait detection. I can tell you about her outputs. She has, in the last 10 years, secured an amazing figure of over £10 million worth of projects at UKRI, EU, and IUK as a collaborator and PI. And she has over 100 technical journals, over 100 academic service goes even wider. So she is a reviewer for has been a reviewer for an extensive list of IEEE and Elsevier journals. And she has been a panel reviewer for NIHR and EPSRC. She's been a reviewer for a range of international conferences. Now, outside of university, Sandra has interest in good food, good beer and wine, good company, and I believe good horses. So it's LSBU's good fortune that we have her with us. So please join me in welcoming Professor Sandra Dudley to deliver her inaugural address.
Okay, so thanks God, I haven't spoken to this many people in so long. We don't see that many students in the lab. So I hope you can all hear me. I have quite a projected voice, so I'm not sure if this is necessary. But as the inaugural lecturer, and the first one I came to was Perry's, and we said in the School of Engineering we'd sort of go down the route of food and where we come from, etc., etc. So I'll maintain that as best I can. And so I'll try and go through a bit of how I've got to where I have, and then I'll talk a little bit about where we are now and a little bit about the future. But what's really important is, through it all, it's the people around us that make the job easier, and it's how we work with them. And so a lot of these slides are the benefit of working with others, and they're here tonight, a lot of them, so that's great to have. So hopefully things will kick off. So learning outcomes of today's I'll cover a little bit on the background. Accomplishments, depending on your idea of what accomplishments are. Friends made on the way, current research, and my God, we made the biggest mistake of my life. A bit of a summary, and obviously with the new way that we work with students, a survey will be provided and they will give me feedback on the next slide. So where am I from? A bit about me. So I'm from Ireland, Republic of Ireland, depending on your, oops, there, go back. So I'm from the Republic of Ireland, I'm from a little place called Munaviog in Irish, which means small shrub, Osqualia. But when the English invaded us, they didn't understand Irish, so they called it Bagnestown, because Lord Bagnall lived nearby. But we have the second longest river flowing through my town, called the Barrow, absolutely stunning. And we have fishing and everything that goes on there. But we have a cricket pitch, which is very unusual in Ireland. And because the hospital's down the road, we've got the best cricket team. Not very many Irish guys on, but Sri Lankan the best cricket team around. It's very hard to pronounce, but it works well for us. You might not know this guy, but his name is John Tyndall, Tyndall Institute. He was born just outside Bagnestown. He was one of the first to note greenhouse effect, so that carbon dioxide and water vapor absorbs heat. But he also, importantly for me, noticed that the laser's off door, when you pump water out of a pipe and it goes along and you put light into that water, the light bends with the water. And as we know, well, not a lot of you know, but that was the basis of fibre optics. So he was a famous man, and he had this tiny little house he was born in just outside Bagnestown, and they knocked it down to build holiday cottages. That's what physics means. And we're quite famous in my town for horse racing. So I a drain on my finances because I have to send money home. Not because I'm down in the bookies, I know I left them lockets in Europe. But this is this year's Grand National winner, Noble Yates. He won, so he's been trained just outside Bagnestown by mum and his family. And then my claim to fame is that's my dad, my sister, and another Mullins, because you can't really do much horse racing without Mullins. And we came second in the county hurdle about 6 years ago in Cheltenham, which was the Cheltenham Festival, which was massive, and we still live on that glory. But it was 33-1, and it kept us going for a long time. It kept those horses in the hay for a long time. But it is a drain. My sister's a school teacher, and you can't really live on it pretending to be anything else. And then I have this wonderful mother who stayed at home, looked after us, worked, never got to retire, we worked from home, we never do. And our favourite dish is bacon, cabbage and potatoes. If you're vegetarian, which my sister is, we just get rid of the bacon and we just add more potatoes and more cabbage. That's it. There's nothing fancy. My mother got into exotic food one time, tried to put pasta into soup. My father was having none of that. It was unbelievable. That's not working as food. So we had major discussions over that. But it's a lovely part of the country and it's a really beautiful part of the country to visit. It's really lovely. Actually, John Booker, I think your uncle lives just around the corner. Right, so I went to Essex University to study. I really wanted to study lasers and physics. And one of the best universities in the country at the time was Essex University. And Ireland was strange. It's a beautiful country, but you don't really hear of the famous scientists. And I walked into Essex University and I ran into Nat Balkin, Brian Ridley, not Spike Milligan, that's Mike Adams, Professor Mike Adams. And Nagy was into what he called sexy electrons, hot electrons. And so he was making them hot and he was trying to see what would happen with the spintronics came out of that. Brian Ridley was one of the first people to notice negative differential resistance. So you have a semiconductor material, you put an electric field across it, and the electrons should just get faster and faster and faster because you're putting more field across it. But what he noticed was they don't keep speeding up, they actually start to slow down. And what's happening is you're heating up the material and the impurities are becoming important and the electrons are banging off the impurities and they start to slow down. And that's a very shoddy way of saying it, but I don't want to make it a physics lecture. And then Mike Adams, he was a pioneer of lasers with BT, Essex University and British Telecom had a big partnership. And he was a fantastic man on the theory, rate equations, we used to call them rate equation 1. And what he didn't know about lasers really wasn't worth knowing. And then we had my old boss and still my friend, Stuart Walker, who wanted just everything to go faster. And he was more on the electronic side and I was very much a physicist. And I have a great relationship, we work very well together. And he guided me through the PhD and the postdoc, and he still guides me, which is a lovely thing. But Essex University, apart from being a great university, was famous for these towers.
Yeah.
Yeah, do you remember? And the greatest wind tunnel I ever experienced. But they were famous, not because they were towers, but they were the tallest structure, I think, in Europe that was not supported by steel. And the only thing I vividly remember was everyone saying, if you lived on the 14th floor, don't wait for the fire brigade. Get out, because there's no one going up to the 14th floor to get you. And obviously, students every Saturday and Sunday night we were out standing around there in the bloody cold, some of that pizza on. And thank God the top bar was managed by an Irish guy. And the Guinness was delicious. So it was lovely. So I had the Guinness. Guinness is always good, so I was quite happy with a smiley face. And I happened to meet my future husband at Essex University playing football. We discovered AstroTurf. And he introduced me to pasta, Italian man, Riccardo Russo, and he's a psychologist. And he introduced me to pasta, pancetta, which is bacon, so happy again, parsley, mushrooms, Irish stuff on the Italian plate, and the passion they have for food. And I said to my mother, you wouldn't believe who I met. And you know there's bacon and cabbage. I ain't going back. It was delicious. And I remember going out with them all and going to a house for a party and they had salami. And I didn't like the look of salami when I saw it first. And they said, no, put it in 50 chopped bread, wine. I'll never forget when I ate it and they all were cheering like I just scored the goal for everything. It was incredible. So I have to say between the degree and the PhD, they were the happiest years of my life. The freedom, I thought. Like the one thing, I know Brexit, I'm not happy with Brexit, I'm sad about Brexit. But there is no better place in the world to study than England. The freedom, the ability to go into a skip, find kit, stick it up, have a go, and real science is still appreciated, and it's really, really lovely. So my PhD, and I remember Steve talked about it 2 weeks ago, about serendipity. Well, my PhD was about semiconductor lasers, and I was working on designing optical communication system, but I was looking at creating these lasers that would take in an optical signal, right, from the right to the left, let's say, because this thing's working obviously with the screen. And you take in an optical signal and it would regenerate it, reshape it, and retransmit it. And so what you have, I don't know if this, can you see that? Yeah. So what you have is a normal laser. So a laser is a device that gives you, for the size of it, you get a massive amount of optical power out at a particular type of colour. So we say red, communications, we love red. And I was working with Sheffield, and they were growing the laser for me, but then I had to process it in Essex. So what made this thing a single section to a two-section laser was I had to etch down here with a bit of acid, but I wanted to maintain the laser itself working. So what you would effectively have is you would have this section acting like a normal laser, because I would bias it and say you bias it with 50 millimeters. And I would not bias this section. And this section is acting like an optical sponge. So on one side you had light being pumped, and on the other side you had this sponge that would absorb the light until it saturated, and then it would release the pulse. And that pulse was happening at gigahertz, right? So you had this optical pulse happening. And I was delighted with myself. I was working with a guy called Eugene Bruton, who was from Nottingham, and he was Russian, and he liked my work, so that made me feel even better. And I was working away on it, I had the pulses going, and I had the light shining, and the optical generation, and I was about 6 months before the end of my PhD, so I was just wrapping up some experiments, and I was about to start writing on page a day, you know what I'm saying. And so I was sitting in the lab with one of the technicians, Terry, and next day I was working about 2 gigs, and this had nothing else connected, and the laser just locked on. If you put in an external signal, it would lock to it. And the laser just locked to the signal. Oh no, because it shouldn't happen, right? And I ran outside, and there was a young lad sitting in the common room. What are you doing? A great big mobile phone, you know, the size of that. What are you doing? You could shout at students then, right? Get out! Where the bloody hell do you think you are? There's experiments going on. Get out! You know, they look at you. And out he went. And I went back in. I thought, there must be something good in this. This is something I wasn't expecting. And I went back and I started looking at the laser itself. And I did a little bit of sums. And it was just that, whatever way we had cut the laser, it had behaved as an antenna. And it had taken his mobile phone signal. I just happened to be doing the frequency that was the same as his mobile phone, and it locked. And that turned me from optical to radio physics. And I then took my piece of work, that was purely optical, and I made a few antennas, and I put the antennas in, and I tried the experiment for real. Put the experiment in so you'd have what we call subcarriers, so you have a carrier, which is a regular frequency, which you can see here, this one here, which is about 1.6 gigs. You put a data rate on it, 100 megs, just for example, and you put those two on and you get a summation of the two. You put them through the antenna, stick out the antenna on the other end, hit that into the laser, and then do nothing on the other side. That should just absorb and let go, absorb and let go. So the laser is naturally self-closing, and the two could lock. So I went from tunable optoelectronic bandpass filtering with optical only to direct off-air detection. So we had radio optical regeneration systems. So absolutely thrilled. I didn't know which one to write up, and so that was worse. So I said, no, well, write that one up because I'm nearly done, and we'll look at this as well. So it was a very stressful time, but an absolutely amazing time. That time you had to do modelling and experimentation. You couldn't do experimental and no modelling. You could do modelling and no experimental. I couldn't even understand that. And a lot of the modelling work was telling me that exactly. So we had a lot of modelling work. I had done a lot of work on chaos within that laser, which you could get chaotic behaviour, but you could tune it back to being unchaotic. It was just really wonderful work. And the one great thing about Stuart, and I didn't think of it at the time, was he didn't interfere. At the time I thought it was just bad supervision. But what it is you know as much as your supervisor at the end of the first year. The second year you go off by yourself because you've done your literature review, you should know more. So they're looking at you for the answer. And that was great. And also we spent a lot of time building up the lab, and it was a really wonderful experience. And then just after that, BT came calling, and I was offered a post at BT, and they wanted us to go to Market Shooties, and I didn't really want to go to Market Shooties because I was a poor undergrad, a poor postgraduate PhD just finishing. I hadn't got a car. Market Shooties is a long way from Essex, and I didn't want to drive all the way up there. So I had done up the lab at Essex, and I said to them, why don't we just call this the BT lab for the sake of the project, and then you give us some kit and we'll do it, and then I'll walk once a week to see. And they were really good about it. And that's one thing I've maintained with the industry. It's really important to just try and get as much out as you can and try and collaborate that way. So what BT were looking at the time was they knew fibre was coming. They didn't think they would put fibre to the home because it was just too expensive. But they could get fibre to the cabinet. And so if they got fibre to the cabinet, which is the cabinet is the little box at the end of your street, if they could get fibre there, they had copper from the box to your house. But it was very expensive for them. It's quite high powered, and if everyone wanted broadband, and this is 10 megs, it was way ahead of its time. Some people don't even have that now. And they wanted to see if they could, not for green reasons, but for financial reasons, could they reduce the power. And one of my little characteristics is, I think as a physicist, probably you always go looking in the old books because there's nothing that hasn't been invented already. It just was at the wrong time. So I went looking, and I found this wonderful book on transformers. And the one thing we could find in the lab that combined the electronics people and physics with transformers, we all love a bit of quality, we were grand with it. And what I thought was, if we use transformers as passive components to split the signals, that drops the power enormously. And then I ran a company called Maxim at the time, and they gave me all these little chips because they were very interested in it. And we hadn't got to the point of surface mapping yet, so we could still solve it by now. And I built this system, and it took about, I'd say, 2 years to get it right, because obviously it's not just an laboratory work, you have to get it right from the company. And we demonstrated a 90% drop in power per customer at the cabinet, which was a world record. We posted that paper in Second see, and we had a paper at that time, Journal of Library Technology. And that time, to get your paper published took about 8 months. So I remember ASAG going, everyone should be publishing 3 or 4 papers a year. And it's like, bloody hell, 20 years ago, that was once a year you get a really good one, And so that was a fantastic job. I was really proud of that. And BT wanted us to stay on and do more work, but I really wanted to, stupidly, because you don't know at the time that you are having a ball, I wanted to be independent, I wanted to do my own thing, I wanted to get branch out. And so I came down for the first interview I ever had, and I'm not an adventurous person. The first interview I ever had was down here, came here to interview, and sat down, had a wonderful interview, met really, really nice people. And I was telling them about my research, and Bob Kay, God bless him, he was really keen about my research. He said, okay, look, his polite way of saying, we're very keen about teaching here. And I said, yeah, I know. And he said, you haven't done anything. No, but I'll be fine. And we do a lot of teaching here. We teach part-time. And he was trying to tell me, I said, look, give me a lap. And if it's empty, it's okay, because BT have promised me this, and I'll get stuff. And we'll start. How naive I was. But they let me start, and I said, just don't, let me prepare for my teaching. So he said to me, don't worry, when can you start? I said, I'll start in August. There's be no one around, I can get my bearings, and then I'm going to be teaching for a while. So he said, no problem. So he brought me down, I came down it's called August. Went round, and he showed me a lovely lunch, and I sat down and got the stuff going, and I just realised then suddenly I hadn't a clue about the English system that you post 92 you had. I was so naive, I didn't realise there was so much difference, really. And I sat down, and next thing, Bob came in and went, about a week into it, he said, I made a terrible mistake. You're teaching next week, and you're teaching MSc networks. I'll never forget it. I said, nothing about networks. Nothing. So I looked at the internet and I looked at a guy called Tannenbaum, who was just fantastic. I emailed him, he had notes, and he had a book. And I said, right, it's a page ahead of the students. And I have to say, when I talk about networks, to this day I hate them. I would do anything but networks. And I had one PhD student who was insisting on doing it. I said I'd have one, but really, I'm not seasick. But the inevitability of paying from this was my naivety was that I worked on my first time grant idea with Stuart. And I said to Stuart, I knew I couldn't keep up with the optics simply because I would never have that type of lab down here. But I said, I do like the wireless, and I'm very happy to do wireless. And that would find me a niche. And then I'll work with him on complementary stuff. Because once you leave, you become the enemy, and that's the end of it, you just have to get used to it. And so I wrote my first time grant, and I was told 3 reviewers, and I spoke to a friend of mine, John Rich at UCL, I spoke to Stuart, I was working with Ricardo, I was trying to get everything right, and they were really impressed with this first time grant I'd written. It was all about radio over fibre systems, but it was about looking at chaos and self-put scenarios, everything I'd done, so I wasn't asking them for something different. But I was going to concentrate on radio. And I had stuff from BT, and there was a company up in Markishmead at the time called CIP, Centre of Integrated Photonics, and they came on with me as well. And I sent in the, whatever you call it, the grant, and I was waiting ages. And I was ringing Stuart, and I said, I don't know. And he said, look, knowing yours, Sandra, they've missed it, they lost it. And I said, okay, I'll ring them up and find out. So I rang up, and they said, no, we don't have all the reviews back here. I was supposed to get 3. They came back a week later, on the dot, 9 reviews. I opened up 8 of them, and on the bottom, on the letter, it said I didn't get them. And I opened up 8, and it was 5 and 6. Excellent work. Bit worried about IP, that should be fine, just go back through them. And 1, number 9, 1. And it said, good researcher, has experience in the field, but this work should be done cleanly. And I just couldn't believe it. And I know what it bloody was. And I couldn't believe that you could write that and you could say that. And that was a massive shock to me. I suddenly realised, I've been naive. And Stuart said, do you want to come back to Essex? And I said, no, I'm taking a job now. I can't be disordered. I'll do it. And I'll find it. And if I'm supposed to be good, I'll swim. I'll just swim a bit faster and I'll get there. And so what I'm trying to say is, I'm not whinging. What I'm saying is these bad things can happen, but they don't stop you. Yeah? Sometimes they're the idiots and you're not. And I know 99% of the time you feel you're the idiot and they're all brilliant, but sometimes they're wrong. So I started looking at, I was down in London, and I was thinking, okay, what can I do to avoid bringing her apart from, asking a few friends to go and see her. I thought about London Underground, and I thought about, okay, I'm interested in the wireless, I'll have a look at things. So I started, and I hadn't got a lab here, so I was popping up to Essex, because I live in London, so I was popping into Essex University, I was working in the lab, and I was coming down here to do my teaching, because I didn't want a gap in the research. And I started looking at, let's say, hostile environments. And I noticed there was a lot of work on older leaky feeders, and it was low data rates. And I thought, well, if you just replace them with fancy cables and put some holes in them, I wonder what would happen. And so it's very similar to what would happen in optics. In optics called Bioengineering. It's the same principle here. And we were putting the holes in the antenna, in the cable, and we were creating antennas. And at some point, I found a region where I had multiple wireless areas of interest, so 4 gigs, 6 gigs, and 2.4 gigs, which was Wi-Fi, WiMAX, LTE, whatever was happening at the time. And what I was interested in was putting wireless formats over optical systems. And I found, we built these things, so literally I put a copper sheath over these, and I would move it along by hand, and I would find at what point we got this to work. And so it was about 18mm slots. We were going with scalpels along the cable. And did that, and set up the system, and got 1.6 gigabits of data down to leaky feeder, which to this day they still don't do that. And Tube Lines and London Underground were really, really impressed. And that was the future. I thought, okay, I can do this, I can do hostile environments. But I realised that I hadn't the capacity. I didn't have a PhD student. I didn't have a lab. You know what I mean? I was going back up to Stuart every 10 seconds to go, I need to borrow this, I need to borrow that, I need to borrow that. So what I then decided, okay, bide your time, do a few years of papers. Everyone said, calm down, get your PhD students going, calm down, everything will come. So I would still say that to new recruits, calm down, everything will come in time. But you can see I'm hopping because I'm trying to avoid X, I'm trying to avoid Y, I'm trying to find my own way. And I then thought, oh, there's another form that works that I particularly like, and it's called ultra-wideband. And that was a bit of a game changer for me because there was two types of ultra-wideband. There was OFDM ultra-wideband, which is what we transmit for data rates. And then there's impulse radio ultra-wideband, and the two together in the same system. And I started this chap with our technician, Terry. And I'm very proud that I got him onto an MRes because the University of Essex wasn't really supporting that, even though they said they would, but they didn't. And I got him onto an MRes at Essex, and then I got him through a PhD. So I was really happy for him because he was a very, very bright man, but didn't have the same opportunities as other people, and he deserved it. We always called him McFaraday. And he's absolutely fantastic, retired now, but really great. So he was doing his, I think, MRes at that time. So I was helping out, and I was going up to supervise. And I wanted to see whether this UWB would be the new way of walking around your house and just having wireless everywhere. That wasn't Wi-Fi, because Wi-Fi wouldn't give you that bandwidth of data that you would like in the future. So these ultra-wideband boxes were doing that, and I was working with a couple of companies, particularly one from Israel, it was very good. And the difference between this ultra-wideband is, so this is your narrowband, your Wi-Fi. The ultra-wideband is extremely broadband, so you might go from 3.1 gigs to about 10.6. So it's extremely broadband, which means the power is low, so you have this wireless flying all over the place, but it's not affecting your health, it's not affecting anything around you, it's not affecting you or anybody else. So it's a very safe microwave type of system to use. And that's where we went with that. And that was the highest data, 480 megabits of data going through just at the edge of your house. But the interesting thing we were doing is taking the wireless format, not trying to make it into an optical format, which is what optical people do, but keeping the wireless formats and putting them onto the optical domain, which was a big change because I knew wireless was coming and they had to accept wireless was coming. And you were talking to optical people, they were going, forget this wireless, it's a fad. Where are we? You know, we have now compatible wireless and fibre systems. Fibre is different, but wireless can take over for rural demand lives and look at 5G. So I was still publishing, but I wasn't getting the grants. And I was really, getting frustrated at this point. You can only say your institution, you can only say what at some point. You've got to try and catch something and get it and put the effort in, and it's a lot of effort. You do get tired, but you keep going. And I was lucky because I was trying to work on the other radar, and I thought to myself, well, okay, we've got big broadband in the home. Why don't we think, what if you could, I was a big Star Trek fan, what if they can understand how you move in your home? What if you can understand that you're doing something with your home, or you need to do something, and you don't have to use your phone? The apps weren't important at the time, right? Apps explosion is 10, 15 years, isn't it? So, go back further, it's not really there. And what you're talking about is you're moving around your home, and I can make the house work for you without you having to do anything. The only way, and then not wear anything, because my husband's a psychologist, and the minute you put that on, you're going to change the behavior. So I said, we go for wireless and you do something like that. And along came Mohammed Kabani, who was doing imaging at King's, and he joined Southend. And it was the first time I had someone to talk to. And I was telling him about this idea I had, and I started to write the grant. And I thought the guys at Essex Psychology, I asked my husband to get on board because of the psychology side of it. I knew if we were going to go for it, we should go multidisciplinary. And there really was about whether the user would like this type of wireless and all. And then the idea of adding, at that time we called them agents, where it was AI that would understand what you were doing in your home, what you wanted. So it would learn from your behavior, turn down the thermostat, turn up the stuff, try and reduce the cost in your house. without you doing it. And we would concentrate on the radar. My team would concentrate on the radar. One side of Essex would concentrate on the agents, and the other would do the end user. I wrote that, and I asked Mohammed to be the PI. And he didn't want it, but he said he would for me, because I did not think I would get it. And we got that grant, and it was 1.7 million, it was huge at the time. And it's, we were so happy to get it. I knew then it's the idea. You just have to get the right idea and get it to the right people, and they'll like it. And so that was the first time then we could get the PhD students in, get the researchers in. We could fill the lab with people, because people is what makes the difference, and people are what give you the capacity. And it's a very boring life when you're sitting there and you're talking to yourself. And it really changed the dynamics of our room. And so one of the really good papers that we had, when we went for the energy buildings, was on that work. And that was demonstrating that we could recognise kettles and toasters and laptops, and we could monitor people moving in and around rooms without touching them. And we could understand occupancy, direction of travel, how many people, what they were doing. And Robert started his work, he was doing MNG at the time, yeah. And, and we have a few, Navid is here, he's there doing research with us. Navid is one of our PhD students, Amir was one of the postdocs, and then there's myself and Mohammed. And then the team starts growing, and other people arrive. So Suela arrived, and she was in sort of the same boat as me, but I was maybe 2 or 3 years ahead of her, and I was telling her not to worry. It was a big win, and oysters, our market, good news, this is right here. And just people bring new work. And so the friends I've made, the colleagues I've had, the students, I don't hire many PhD students, but I end up keeping them, and they stay as postdocs. And I like that atmosphere, so people stay for a long time, because research takes a long time. And I prefer not to have a big turnover. So I'm always trying to work with the industry. Poor Gianni. Gianni's here. He's UBT. He's one of the star companies that we've been working with from Italy, who's now come to London to work with us. And they do, I can't talk for how, they do breast imaging with the same ultra-wideband work, but it's non-ionizing. So any young girl to older woman can have it, and they can have it as many times as they need. And we have that, system in our university, and it's there, it's a fantastic system. And we're really proud to be part of that with Jen. And those people have come through, and the PhD works that we've developed on with Matri and Shomer are there, they were big parts of the PhDs. And Hafiz went back to Pakistan, he was working there. This was Ola. He wanted to do networking, bloody hell. And I was trying to say to him, okay, it was painful for him to watch. But that's my most cited paper, and I don't have any interest in it. So it's quite, it's annoying, but I was glad for him. But he brought that type of characteristic, which was really important when we moved on to the other stuff. But we also do energy, and I just wanted to mention, because during COVID, we never got to wish our students well and things like that. But Matri, some of the work we've done, Matri won the best paper at a prestigious conference, and then she got accepted for a journal paper in applied energy, which was a big journal paper for us, because yes, the advanced materials people 4-star papers all the time, but us poor physicists, engineers, so 2-star. No, not 2-star, don't talk about 2-star. But we get our impact factor a little bit low, so we have to be very careful. But she's done a great job, and she brought the AI work and herself and showing, and we've been able to work with companies and find out ways of taking what we do in time series data in the health side, but also applying it to energy, because the two are very similar. And we have grants going in both directions. And don't worry when people say to you, oh, you should concentrate on one or the other. You live one life, enjoy what you do, and if it's 10 different things, so be it. Who cares? If you publish a paper on each of them, what does it matter? So we started looking, my house then became a test bed, and we started looking at how can we recognise what people do. So that was the big grant we got. We worked on that, and we understood how people were moving, we understood what they were doing, and the AI started. And then we thought, well, why don't we think about how people are moving? And are they active? So one of the grants that we had and that brought us to the European project, was how do we identify activity at home? How do you know? When people say, old people are not active. Well, activity is, it's perceptual. So people getting up all day, doing the dishes, hoovering. For an 80-year-old, that's quite active. Yeah? And to say that they're doing nothing is a bit demoralizing for them. So we looked at, well, how can I recognize what the movements are? And then if I recognize the movements, how do I then inform the person that they're doing well, or how do I understand habits are changing? So we're moving towards that. And we started with the radar, and to be honest, if you looked at the system, I was only worried about the radar, but then I noticed there was no bloody infrastructure at all to go behind the radar, so you had to go back to network, and you had to get everyone involved, and you had to build the whole thing just to get that bit working there. Because you couldn't buy anything off the shelf, it was specific to us and we needed to. So that took ages. But what we started to do, so you've got these pulses that come out of the radar kit. So this kit here will send the pulse, it's very quick pulse, and one will transmit and one will receive. And it sends out, show me when you do a demo, but please go. But you get a sort of donut shape. That's just, and the antennas tell you that's their formation. And that comes back. And then this little guy transmits, this little guy receives, and then you have signal processing. And then beyond that, you have a big, powerful laptop, and you do all your signal processing on the back of that to recognize it. We've also been doing it with microprocessor and Raspberry Pis, and we've been putting them on around. So we started that, and what you end up doing, you get this book, but the information is in there, and what you've got to do is try and find out where the information is and how is it relevant to you. So we start looking at patterns. So for example, washing the bowl in the kitchen sink, watching TV in the living room, walking to the kitchen, brushing teeth, and you would keep doing this where you were training the system, and you were training to see if it understood the actions and remember the actions, and then you would get it to do those actions and see if it recognized them. And then you would get someone to do random actions and then see if they recognize that. And then you knew you had some success. And we were doing it all the time in live environments. I didn't want to do it in the anechoic environment. The anechoic environment is a perfect wireless environment. There's no reflection. You need to do them in the real environment, otherwise what's the point? So that's what we were trying to do. So I looked like a bit of a zombie walking around half every evening, banging out the window, the curtains open, we were just watching me go around. But I had to train it, so that's what I was doing all day. And that moved us towards gait, because we were very successful at that. But then we thought, well, why don't we look at the idea of gait? And I know I'm going through this quickly because it sounds like it's quick, but these are taking years at a time. And you have small teams, you don't have these big Bristol machines, imperial machines, you've got practice students. And we started looking at the idea of gait. Now, I didn't know anything about gait, I still don't know anything about gait. I know location sensing, and we've been doing, I got shown why I asked him to come and look at the PhD and he came along. And I remember the first year, his face, and he was struggling, but he really, really pulled it around and did a fantastic job. And what we looked at was, okay, gait in itself, if you're doing it properly, is a very expensive business. But what if you could deploy a gait system that would help kids, for example, that had prosthetics, and you could have eventually an intelligent prosthetic that would then respond to this, which self-adjust itself, and that work with that child, that would have it longer, and it would work with them. Now, it's a dream, yes, but it's not to say that it can't. Other people are doing it, but we can do it without all maybe the dots on top and touching the skin, and that's what we hope. And so we're at a point now where we can do that, we can measure gait, but now it's at a point where now we need to collaborate with others. So part of this today is to talk to you about collaboration. So how we looked at it is so Shoma was doing all his PhD on that, and we started looking at the idea of spherical coordinates and vectors, and the idea that this generates this donut shape, and we look at the idea of X, Y, and Z in terms of coordinates to see how you walk towards it, how you walk away. Now, it's not random. You must behave as you need. Yeah? You don't go into a measurement lab and walk all around the shop. It's the same with this. For that particular job, it needs to be, at the moment, in that research, it has to be spot on. But there are we hope with more people and more work, it'll eventually be random. But to do what you wanted to do against a gold standard, I think you should be as close to the gold standard as possible. So what we've been looking at is creating this mathematical processing about looking at the angle between the thighs as you move between the hip and the thigh, how the feet, and working out the body in particular regions. So Shomo did all his PhD on that work, and it was fantastic work. And we've had really good papers and really good feedback from the reviewers. And the spherical coordinates has been really, it was sort of a simple, but it worked and continued to work, and we couldn't find it not working, and it's been really, really a nice approach to it, which means you're reducing somewhat the signal processing power, which means it is deployable much more easily. So Shomo is going to try and do a little demo. So what we have, if I give you a step, what we've done in all of our work is we have our radar kit. So this is an anechoic environment. So what you do is you have an environment where you get no reflections, and that's where we started. And then this is called the Connect system, which is a camera-based system which people use. And what we were doing was comparing our two. Because how else do you compare? And we then correlated what was happening on the Connect with our system. Now, the Connect is great. It's a camera-based system, but it only works about 2.5 meters?
Up to 4.
Up to 4. But it doesn't do through wall. So, for example, you don't need to be in the same room as this to make it work. So that's what's really important. And the fact that it is in the camera. You forget that it's there. You just get on. But we were looking at it for physiotherapy, for rehabilitation, for gait analysis. And so I think you're going to try and give a demo. We're having trouble with HDMI, but I'll hold on to it to one end. So I think it's important the person who's been working on it for so long demonstrates it. He might be a bit shy, so give him a chance. And I'll plug this in.
This is the interface we use to connect this one. And these are the propagation delay we have to mention to fix the range or set the range. So within this propagation delay, it can only work within 3 meters all over this space, because this is omnidirectional. So whatever you do within the 3 meters, it can capture the physiological and the biomechanical process. It can capture. So
we picked that 3 meters simply because you want to avoid interference from other people, but you can extend it or shorten it every time. But we've been working. Yeah, that's right.
So yeah, I start a scan, and approximately this space is 3 meters. So I'll walk in front of this back and forth and see what happens.
I have no interlude music. Don't be self-conscious.
So this is the interface, and if I start walking in front of this, it takes time, and you can see the red dots. Those are the detections basically. So this is the whole pulse length of 3 meters, and if you work within the range, it collects the point and measure a threshold to detect the physiological and biomechanical process. So, and you can work long, and then you can just, I'll stop this scan and show what it looks like. So I have built this graphical user interface to measure the gait and to use with artificial intelligence and machine learning. So this part is with the pre-existing data. We always take the subjective data, the gender, height, the length, thigh, and the shank from the ground.
So we have a database.
Yeah, we have a small database, and we are aiming to increase it.
And this is why we want other schools to.
So if I go to the gait analysis, so this, I need the tripod length from the floor, and the height of the hip and height of the shank as a subjective input to start the system.
So the shank is this part.
This part and the thigh and the tripod. So if I set there, this is approximately 1 meter, and hip is 1 meter, and knee is at 0.5. So when I stop the system, it's collected the data and stored into a Excel file. So I'll start processing this one. It will take a few seconds. So this is actually the point cloud of physiological motions in the 3D. That's the most important part of our work. It's in the 3D. This is the first ever work to represent the physiological motions or movements in 3D from the ultra-wideband. So it's actually inspired by the anatomical reference plane, the sagittal, frontal, and the transverse. So the x-axis actually represents the front side of your body, and that represents the sagittal plane. If you consider the y-axis, that is the frontal plane, and if you consider the z-axis, that actually represents the transverse plane. So actually, we built from that concept, we built the x, y, z coordinates, and if we consider the coordinates, if we have the coordinates, that means it has the magnitude and the direction, and we converted the whole thing into the vector algebra. So we built the mathematical model, and we take these two lines as a region of interest. So that first red line in one is the hip, my hip, and the second one is in my knee. So whatever the coordinates within that region of interest. So if I pick one point from the thigh and one point from the sand, mathematically if we extend those two lines, it will intersect in the infinity. So we can easily calculate the angles or other parameters for this. So we have calculated knee, hip angles, step width, and step size, and the total travel distance.
So this is continuously picking up what Shomu has done over time. Yeah, it's not the final number, it's continuously following what he's done. That's what we're looking at. We get this little angel shape at the top left, which shows you the movement and how the movement is superimposing itself on time, in time, and all of those coordinates are matching that time. And what you're trying to do is extract what those coordinates are that you're interested in. Yeah, and that's where the bloody hard work comes.
So, as gait is not only the lower limb movement, it also coordinated from the nervous system, musculoskeletal movement, and the cardiovascular. So, when I'm working, actually my upper limb is also working. That means the heart, lungs, and my hand also coordinated with that process. So, we can also track that part from the 1.5 to 1. If we put our region of interest for that part, we can easily track those motions and calculate the other parameter also. So I'll just show you from the same file how we can calculate the vital signs from my working. So the tripod name was 1. This is actually my shoulder height. This is the hip. So I'll use the same file, and the same 3D motion will come, but this time the region of interest is from the shoulder to hip, so that we can track the hand, lungs, and the heart rate. So this is actually the same motion, and this time we are looking for the upper limb, which integrates the hand movement, lungs, and heartbeat. So we know the azimuth and the elevation angle. So we can actually differentiate between the two parts of our body. Like the 0 to 90, which is actually my left hand side, and 90 to 180 actually my right hand side. As I'm walking back and forth, it's a mix of heart and heart rate, breathing rate, and the hand. But if you just stand there, you can easily measure the vital signs of a person without using any non-contact devices. So there are 3 different movements. So 0 to 3, 0.3 to 0.5, which is actually the average or regular heart rate, the lungs rate. And if you go above towards 1 to 1.5, this is the range for the heart rate. And if you go above, which is 2.5, which is actually my hand movement while I was working. Yeah. So, yeah, these are the parameters we have calculated.
So you can extract heart rate for that person, you can extract the breathing, and you extract the pace. You haven't touched them. And the way we can extract it is fine, but it's really important that it makes sense to the people who are. So these things wouldn't make sense to you, but the colours are what we're looking at. And then we look at those colours, and then we get a particular rate at the time that that person was moving forward and back, and we extract that. And then we base that on additional information from machine learning and AI. And so that's how that works. I'm also conscious of time.
Yeah.
This is what we call a normal gait. We also. Oh yeah. Thanks, Sean. Sorry, thank you.
Thank you.
So what we also have is abnormal gait, and we've worked with a lot of people and bring someone in and just get them in for abnormal gait. And we can distinguish between, so we worked with the spastic gait, which is driving the leg across, and we worked with people remote, how to use this and understanding that, and seeing the gait, seeing the difference. And what you do see is that you have massive widening of the three-dimensional plots. Obviously, the radar is picking up a wider movement. Radar makes a movement. And then you also get to see at times a massive change in the hip angle against the thigh, which is telling you, and the AI that we perform picks that up. And that happens and happens again. And that diagnoses that type of abnormality. Now we can diagnose those, we can say that's happening, but we are not physiologists or doctors or anything. We are just a bunch of people in the engineering school looking at that. And the way we want to go forward, how useful is this information? Can we do it? Can we build it with people who do know what they need to know and tune it to support that type of work? So we have these abnormal gait and we have normal gait, as they're called. We've done a lot of research in terms of building a database and learning from that. And we've applied the learning. And we're getting, the last paper we had, the last piece of work we did was a 99% success rate on sensitivity and specificity. So it's there, the information is telling us it's there. Let me see if I can go on. Right, so thank you for listening. I hope it's given you some idea about me. I know I come across maybe as I don't talk too much, but I really, I don't find myself very interesting, so it's nice. It was very strange for me to stand here and talk for a whole hour. I can't believe I've done all that. But we're building on the first three-dimensional, non-wearable, camera-free system. That's what we want to do. I have very high hopes that we can help people who don't have access to these big labs, who don't have access to this type of available in the community that could actually help people, that could help people in rehabilitation. And I think we could, really try. And I've had lots of interest down from Southampton, but I want to work with South Bank for change. I don't want to go outside the university again. I'd like to work with teams here. I think there is potential for mass deployment. I think the idea of adaptable prosthetics, I know other universities are working on it, but I think we have fantastic opportunities to look at intelligent control and adjust for, say, particularly young children maybe, who would need that change in prosthetic over time more quickly. And I think AI has enormously made things work for us, the recognition, the ability to detect changes. But the underlying physics and electronics and signal processing has to be robust. And the only way you can test that is to work with others who are not in your area to see what can you do with it. And that's where, I'm a bit pedantic. I like to have things perfect before I go out, but actually they're never perfect, and you have to go out and work with others. And maybe that's the only thing the professorship has taught me, just to calm down, say I don't know, I can say I don't know now, I won't get fired. So AI is really pivotal, and I really mean that collaboration for us is really important. So, thank you very much for listening.
Right, so I made some notes, but I feel I should start off. Sandra, I feel like you've dropped me in some trouble to implying that I'm using, with my boss present, I'm using a credit card inappropriately to buy oysters. That's not true.
They were gone off the worksheet.
Yeah, what was the other one? That I fire staff, I sack them at short notice. So I feel there's a bit of a clean-up that I had to do at that point, so just to get that clear. But yeah, thank you very much, Sandra. I think, some great insight in all of that. Wonderful story. So I think straight away I picked up it was a really wonderful story on almost the accidental switch from optical physics to the radio. And I think we've seen that quite a lot in a number of different presentations. But it just kind of reminds me of the simple need to be active. Because if you're active and doing things, it tends to be the more active you are, the luckier you get. Maybe the horses, you're not so lucky with the horses.
I try every day.
So maybe
There's me and a couple of the cleaning guys. That's all I see in the bookies.
Yes, so I really like that point. I think as well the link between kind of the optical physics, the electronics, and that clear industrial application, that sort of end-to-end type of approach is great, and I think it's becoming increasingly important. So we see it now with the UK's national R&D strategy, the need to look much more at that fundamentals towards application. And I think that's a great example of, I thought you were quite modest, because I think in less than 12 months you picked up two really major grants. So I don't think this is at all the pinnacle of your work, and I think you've got a long way to go, hopefully to bring in those big grants for the school, to keep the criticism off my back, so I don't have to sack you.
Gardening leave at home.
Yeah, gardening leave, that's right. I'll write that down. I think it's also a great point that you made in referring to both the work of people, sometimes quite distantly in the past, and I think that's forgotten. Sometimes people Google something and it's like the last 10 years, but you can look at things that have been going for sort of 30, 40 years in the past, and there's a great insight. And also to interact with your peers. And you picked out how it was suddenly when Mohammed came on the scene, it was somebody to interact with. I think it's so important to interact with people, and perhaps it's a sign of your strength in terms of interacting with people that we see such a wide variety of people that have taken the time out to come to your inaugural lecture. So I'd like to kind of finish and thank you, Sandra, in giving all of us here your personal insight and reasoning, and really developing your journey to this point, and hopefully it will continue strongly in the future. So the tradition is we don't take questions, so I'd encourage people here to approach Sandra in a few minutes if they want to congratulate or talk about collaboration. As is the tradition, I'm going to go and pick up a certificate. We'll take a picture of us. Yeah, don't worry. And then, we'll take a picture of it. And I'd ask everybody to congratulate Sandra as we do this. Thank you.
It's been lovely. Thank you everyone for turning up.